Okay. Let's go ahead and where we left off. So we're rounding the last third or so of chapter 7. And so we're talking about infectious disease. So after 7, we're going to be diving into 10. So I just posted those to D2L, the PowerPoints that is. So those will be there. It'll be 10 and then 9 after that. So that'll be respiratory and digestive after that point. Also, next week we have our exam. So we have an exam that'll cover where we left off before. I think we got, I'll have to find out what the cutoff was. I think we left off at 5, I believe. I don't think we covered 5 on the last exam. We covered, I think, up to 4, I believe. Okay, 4 was the cutoff because I was like trying to remember. It's like, okay, we were in the middle of 5. We just finished 4, and there was kind of like, because I remember there was one that was right there on the fence. Okay, so that's basically where we left off, and then where we're going to end this time. So this will probably be a pretty clean break with 7. So 10 forward will be on the next one. Yeah. So one of the consequences of not having that last chapter on there is the next one has more. So, unfortunately, but so that'll be 4, 5, 6, and 7. So, so there'll be a lot of work to do, right? So, and hopefully we can get this pretty close to wrapped up, so you have as much processing time for 7 as possible. Okay. Because, and the reason why we don't want 7 on the next exam is because 10 and 9 are going to be pretty big. Those are pretty stout chapters. So you don't want a lot of extraneous chapters hanging on to those really, really big heavyweight chapters. And there's a lot of things going on in digestive and respiratory, and you kind of want to have those in a smaller bundle. Hopefully that's the way to work out. So it'll take a little longer to kind of cover those. So, and we'll see, obviously we'll make that decision when we come to exam 3. But first of all, let's go ahead and finish up and do the best that we can to finish up our chapter here. So we're talking about basically immune system, and now we're talking about the compromises to the immune system, right? We're going after now some of the disorders of the immune system. The first one, of course, the most famous one is going to be HIV, right? Human immunodeficiency syndrome, which basically causes what you really die of, which is the acquired immunodeficiency syndrome, AIDS. So that's basically essentially the crashing of your immune system. So basically your immune system dies is essentially what happens here. And so you have 2 different types of HIV. So you have HIV-1. This is the most common one that we run into, and then HIV-2. The HIV-2 one is mostly isolated to the green monkey in Africa. The HIV-1 is in chimpanzees, and that's common in West Central, and that's the one that we typically run into with us. And so when we take a look at this, because HIV was originally a monkey origin virus, and most viruses typically prefer a host, and so it's not common for viruses to jump hosts, and that's one of the things that kind of protects us from like viruses that attack our dogs or other animals. But some do. In this particular case, this one did. And so it originated potentially in monkeys. And the idea is it probably came from the consumption of monkey meat in those countries. So as they eat that, then the virus survived and basically jumped ship and landed on us. And then it kind of spread from there in multiple different ways. And so ultimately, when you take a look at HIV, they have to have a particular surface receptor on them. And that's true for most viruses. Viruses look for a specific receptor. They have to attach to their host cell in order to be able to make any headway on them. And so what they go after, unfortunately, is our helper T cells. And we've talked a little bit about those guys before, right? These are our regulators. These are the ones that are kind of like making sure we're regulating all that T cell response and B cell response. And you're taking these guys out, and it's very, very dangerous because you're essentially destroying the tactical division of your immune system, right? And that's a surefire way to win a war, right? So forget about infantry, forget about troops. If you want to win a war, take out the tactical brain trust. There's nobody who's able to actually build battle plans, then you have no leg to stand on. You literally have no fight. And that's kind of what happens. They go after those helper T cells. They also go after macrophages, another bad one to go after, right? Because these are the patrollers that are basically protecting your entire body from infection. And so ultimately, as they attack these particular cells, then your immune system slowly starts to diminish and your helper T cell numbers start to decline. And then you'll basically get sick with all sorts of diseases that oftentimes are opportunistic in nature and things that don't occur in a healthy individual, right? That's pretty typical of somebody with AIDS. People with AIDS die of crazy things like the common cold or a flu, right? Something that nobody would mostly die of. But because they have no immune system, they have no defense to it. So there's no way for them to do battle against these particular invaders. And so AIDS is basically the kind of full-blown outcome of the HIV infection. But there's a trajectory, there's a pathway to go through upon infection as you start to move forward to the actual full-blown AIDS idea. But basically, AIDS is the total collapse of your immune system. And that's kind of where you get all these opportunistic infections, like these little peewee diseases that would never stand a chance against your mighty immune system. Now that your mighty immune system is kind of compromised and it's kind of like falling down on its knees, now all of a sudden these little peewee invaders come in and they can finally do away with, well, your immune system and ultimately you, right? So these are kind of the stages that you get to. So ultimately, when you take a look at HIV, which is the red line, and then compare that to the helper T cell count, which is the blue line, ultimately, you get your first kind of infection, if you will. This is your acute phase. So generally at the beginning, you're going to get a big spike of HIV increase. And so you'll notice your T cells, your helper T cells will start off high, but then as your HIV increases, they crater, they tank, and they crash pretty quickly initially at first, right? So there's kind of like a first initial blow that kind of brings the T cell population down mightily. After this, then what's going to happen is your HIV levels will come back down. And this is because your immune system is doing battle against it. So it is actually waging a war against HIV, and it does actually become effective at the beginning. But the problem is because you have a diminished T cell response, it's kind of like you're compromised. You don't have all of your full weapons. It's like playing a game when you're injured, right? You may be able to be functional, but you're not going to be at top speed. You're vulnerable. You're vulnerable to being beaten, right? And that's kind of what it is. Your immune system is still working. It's hobbled, it's injured, but it's not out yet. And so you can see that in that drop in HIV. It's doing the battle. But what happens is it doesn't really quite get rid of the HIV, which normally it does, right? Like with the flu virus or any other virus, the immune system will eventually finish the job. But in this case, what happens is a little bit of a reservoir of HIV is left behind because it's not at maximum efficiency. It can't finish the job. And that little pot of HIV begins to slowly increase over time. This gets you to your chronic phase, right? So ultimately what happens is as that little small reservoir of HIV begins to slowly increase over time, it's going to keep chipping away at your helper T cells. Now, at this particular point, you still have an immune system. But what you have is an enemy that's now inside of you that's not gone. And instead of giving you the mortal blow, what it's doing is it's kind of like picking at you a little bit at a time, like a slow drip. It's slowly eroding away your strength because it's slowly over time taking out your helper T cells. And that's what's happening in your chronic phase. Your HIV count is slowly increasing, but it's just chipping away at that helper T cell population, which continues to go down and down and down. And the lower you go, the more compromised your immune system gets. Generally speaking, it's good enough to maybe do battle with most other viruses. But as you continue to progress forward, you start to see this slow diminishing of the immune system until ultimately the immune system is just not able to function anymore. That's the boundary between when a person goes from HIV infection to full-blown AIDS. Basically, this is essentially where the immune system is not strong enough. You've chipped away at it so much that it's not able to actually fend off any of the invaders. And then what happens is, as that helper T cell population begins to slowly diminish, all of a sudden the HIV begins to take over, and it sees its opportunity and begins to increase mightily as you get to the end of terminal stages of AIDS. And you can see your immune system is basically crashing now. This is where these opportunistic infections will come in, and then they will cut your life short. Okay. So ultimately, that's kind of the trajectory of HIV. And a lot of it is associated on education. Don't get infected in the first place, right? And also is, once you are infected, then how can we slow this virus down, right? So what we want to do is we want to basically slow down that chronic phase, extend that out as much as humanly possible, and fend off those terminal stages where you move into that full-on immune system crash. Okay. Now, there are other types of disorders. So we have sensitivity reactions. For instance, this is where you have an overactive immune system that can cause harm to the body. For instance, allergies is a hypersensitivity situation. If you have an incompatible blood type, tissue rejection, autoimmune disease, those are all types of hypersensitivity reactions. Typically, it's when you're attacking things that are good or that we deem good, right? That's typically hypersensitivity. So in allergies, basically what is good, well, good, I should say good, or harmless. So the allergen, which is essentially what's causing the hypersensitivity, is typically something that's benign, right? Pollen. So pollen isn't going to hurt anybody. But that's not what your immune system thinks, right? Food allergy, same thing. Animal dander. These things are harmless. These aren't pathogens. So they don't harm you, but your immune system sees them and is like, well, wait a minute, this is not good, not good. So we're going to have to go on the attack. Okay? And that's kind of what happens with these allergic reactions. And so ultimately, when you have your immediate response, this usually is pretty quick within seconds of the contact. What's going to happen is your IgEs, remember the IgEs, those are the ones that are basically active, especially when you have allergic reactions, those are going to skyrocket. So those basically will be attached to mast cells and to basophils. And remember, these both are the two cells that release histamine, which is essentially your blood dilator, right? And so when you have pollen, for those of us with hay fever, right, or spring fever, then what's going to happen is it's going to stimulate the histamine. So the histamine is going to stimulate your mucous membranes to start to increase, because the idea is you've got some sort of an inhaled contaminant. So we're going to increase the mucous membranes to catch that inhalant, right? And then that's going to expel it. So that's basically where you start getting the runny nose and the watery eyes situation. So what you're doing is you're increasing the amount of fluid that's designed to catch these inhaled particles and to expel them. And so that's kind of what histamine's job is. That's the reason why you get all runny in the nose and itchy in the eyes and things like that. Watery eyes when you have this kind of pollen-related allergy. So when you have asthma, which is also allergy related, this basically is going to restrict your airways, and that basically creates wheezing, right? Kind of that wheezing effect. You're cutting off basically your oxygen. And so, of course, then you take inhalers that are designed to dilate those bronchial tubes to basically restore the flow of air so you don't suffocate. And food allergies, oftentimes, is seen as sort of like a foreign contaminant. And so you get nausea or reflexive vomiting or diarrhea. Basically, your body is seeing it as a foreign contaminant. It's rejecting it. And so those are some common things that we see. Now, if it's bad enough, you'll drop into shock, right? So anybody who has especially a nut allergy, a peanut allergy, knows full well of this danger because nut allergies are extremely aggressive in nature. And so they'll drop into what's called anaphylactic shock, which is a very quick allergic response and very severe. So basically, when the allergen enters into the body, often entering the bloodstream, but not necessarily always, you'll basically move quickly into a shock place. So what's happening? We're in anaphylactic shock. Well, first of all, what's happening is your blood pressure is dropping very quickly, very precipitous, like falling off a cliff. And this is basically mostly because of the histamine response. So the histamine response is so aggressive that one of the things that it does is it increases the permeability of the capillaries, which basically moves all that fluid out of your bloodstream, causing your blood pressure to drop. Why? Because all that fluid now is in your tissues instead of in your cardiovascular system maintaining pressure. That's the reason why your blood pressure starts to drop quickly. So basically, if you have anaphylactic shock or anaphylactic shock potential, then people who have these issues know full well that part of your routine is carry your EpiPen, right? So your EpiPen basically is an adrenaline. And so what that does, it counteracts the effects of that severe effect of histamine. Okay. So you also have delayed allergic responses that aren't necessarily anaphylactic. And oftentimes these will be triggered by your memory T cells. And so once these are triggered by your memory T cells, these will kind of cause a sort of a lesser reaction, but it's still a reaction. Like, for instance, this is what happens when you get poison oak or poison ivy. You get a reaction in the local area of wherever you touched it, right? Because there's an allergen that's associated with the oils of these particular plants. And so some other ones, for instance, that you'll run into, other issues, you'll run into tissue rejection. This is basically your immune system attacking a donor organ that's saving your life oftentimes. So what happens is it reads the self tags on your transplant and realizes it's not you, right? Because one of the things your immune system is doing is surveilling all the cells in your body to make sure they belong to you. They're looking at your name tag. This is your self tag. When they see that I've got Bob's liver, because I got a liver transplant, they don't see my name. They see Bob's name, and they're going to attack it because it's foreign in nature. And so the cytotoxic T cells will go after these transplanted tissues just like they are pathogens, like bacteria. Now, if you are a transplant patient, first of all, it means that your original organ went to catastrophic failed point. So you're not healthy, right? You're not a healthy person. And so the transplant is designed to extend life and to kind of increase that window and move that forward. However, in order to live with this transplanted organ, you have to have an entire spectrum of immunosuppressive drugs that are designed to keep your immune system sort of quiet and muted so that it doesn't attack your new organ. And it's constantly changing. So for instance, like when we had heart patients who had transplants, we didn't have a lot of transplant patients, but we did have some of them. They were basically part of their life routine, and part of their life was going to see the doctor every month or so, because the doctor had to, and they had like a medications list that was like a couple of pages long. I mean, it had a boatload of medications that they had to take, and the doctor had to sit down with them on a routine basis, and it had to rebalance those medications, because the idea is you wanted just enough dosage to quiet your immune system. You don't want to crash your immune system, right? So you want a healthy immune system to fight off infection, but you want to kind of catch that sweet spot. And it's very difficult to catch that sweet spot because oftentimes it's always moving. It's a moving target. And the doctor is constantly having to adjust medications to make sure that it stays in that targeted zone. So, but I mean, the prognosis for our transplant patients was actually quite good. I mean, their livable window of life increased by a significant amount, decades at times, depending on how old they were already when they got the transplant. But it worked out well. It's just high maintenance. This is what your life is going to be once you get a transplant. You're going to be maintaining that. So a couple of things you can do, like for instance, you can do transplant of different things. One, you could do what's called xenotransplantation, so transplanting organs from other animals. Like for instance, if you do a valve transplant, you can do a pig valve transplant. So sometimes we'll do that. You can also grow some organs in a lab. So we're just beginning that. So that's just a beginning technology that's starting to click in. There were no lab-grown organs in our office. On occasion, we would have a pig valve or patients who had pig valves come in for routine monitoring and things like that. But we have more heart transplant patients than we actually had some of these others. It depends on the nature of the actual pathology or damage associated with the heart. So SCID, severe combined immunodeficiency syndrome, basically, this is one that we run into. And this is associated with an aggressive cell-mediated immunity, where basically it's either weak or lacking. And so in this case, a severe penalty can be accrued from just a minor infection. So just a minor thing can be fatal in this situation. Oftentimes we have to treat this with a bone marrow transplant or with gene therapy. Gene therapy is pretty cutting edge. There's a lot of trial and error associated with gene therapy. So it's not a big thing. Like we never had gene therapy in our office. It wasn't even a thing. However, there were some patients who were beneficiaries of bone marrow transplant. The idea being that you're essentially taking some of those healthy stem cells from a healthy individual and you're planting them in your own bone marrow so that they can take over and start building new, better B cells, right? So, because your B cells, for some reason, are not normal. They're not normal output. That's the reason why you're lacking in the antibodies. And so the idea is you add your transplanted B cells from somebody else in order to create a lineage of healthy stem cells that give you healthy B cells. Okay, and that's kind of the idea. And oftentimes those transplants can actually work out quite nicely. They're very tricky. They're very difficult. Being a marrow donor, I hear, is beyond painful. And actually, I also, because when I was first starting out in the medical field, like as a fresh out of high school, I remember we had a pediatrician, an old guy, Dr. Fisher, nice guy. But he developed bone cancer and he was ultimately on crutches at some point. But he was saying and kind of telling us like, this is like incredibly painful. Just bone pain is a different level of pain that oftentimes people don't really experience because most of us don't ever really damage our bones that way. But it's helpful and it is typically effective. So it's just very difficult to get to. So because all the marrow is inside your bones, so you can imagine what they have to do to get there. Nothing you want to think of, right? Some other types of immune deficiencies that we run into, we can get them from anywhere, right? So for instance, you can get them from infections. So some infections can have actually lasting secondary types of effects. You can get them from chemical exposure. So different types of chemicals can have immunoaggressive types of activities to them. Same thing for radiation. So the primary infection one we've already talked about, right? So HIV is a viral infection that causes AIDS, but you can also have different types of chemical treated sorts of things. Like for instance, if you get radiation poisoning, you can kill the stem cells in your bones if you're unlucky, and that can start to compromise and crash your immune system. Okay. Another thing that can kind of create a little wackiness a little bit are autoimmune disorders. And some autoimmune disorders are genetic and some are acquired. And there's a big spectrum of autoimmune disorders. Basically, what an autoimmune disorder is when your adaptive system, either your cytotoxic T's or your antibodies, attack your own cells as if they're foreign. So this is basically a fundamental breakdown in the self-recognition mechanism. So normally you're supposed to be trained to tolerate things that have your self-tag. But in autoimmune disease, typically it means your immune system is fundamentally breaking down in that identification process. And it's seeing you as a threat, even though you've got a self-tag on you. So even though my cell has a mark tag on me, it sees this as foreign and then goes on the attack. And then the attack of your own tissues is what creates the symptoms of the autoimmune disorder of whatever it is. And so, like I said, some of these can be genetic and some of them can be acquired. A good example of an acquired one, and this is kind of like goes back to our previous slide where we said that some of these acquired immune deficiencies, you could think of a deficiency, not so much of a deficiency or as a kind of an acquired autoimmune sort of a situation, is actually something that I went through, which was weird, but it was triggered by a flu. And so I have what's called cold-induced urticaria, which is basically hives, right? So hives is essentially an example of an immune response towards some sort of an allergen, right? So if you touch strawberries, you start breaking out in hives or something like that, right? So that's an inflammation response to that particular allergen. But mine is cold induced, which is strange. And the first time I heard about this was actually when one of my AMP2 students wrote a research paper on it. And I was looking at it like, wow, that's really weird. And then a few years after that, I actually got it. So in a February, because I used to be able to like go out into the winter and I could wear my sandals out there in the snow. I could walk barefoot out there and it's not a problem. I remember like after working out, I used to do a quick cool down. I used to just like go out there without my shirt on, like in the cold snow, and just start stand out there and just kind of let all the steam evaporate, and it cools me down pretty quickly and not a problem. So I was pretty cold tolerant, cold hardy. But then I got the flu one February, and whatever this particular strain of flu was, basically messed with my immune system. So that after that, and this is something actually we know about cold urticaria, that's oftentimes it's kind of you can get it from an infection that basically leaves your immune system with this particular situation. But now when I go outside, I actually break out in hives. So like if I go out, like after working out, I'm all hot, and I go out into the cold, I'll cool off, but then at some point I'll actually start to itch and I'll actually start to feel the hives actually start to come out. And it looks like somebody just scratched me all over the place, like because I'm scratching, right? Right? Because all over my body, you actually see them and I can actually feel it. The first time I noticed it was when I was walking outside in my bare feet and I couldn't even make it to the garbage can because it felt like my feet were swollen. And they were really red. And it's like, well, geez, normally I could just like walk out there. I could actually walk barefoot in the snow probably about halfway through the yard without even bothering me. But now it's like I can't even walk on just normal cement in the cold, and my feet are feeling like they're getting swollen. And then when I came inside, they would kind of be throbbing and hot, and then they would sort of simmer down. And I realized that that's what I had. I had cold urticaria because of that one flu that I got in February. So that was like an acquired autoimmune situation, right? So that's clearly an autoimmune thing. Okay. So That's an example. So just if you get it, it is a thing. I never thought it was a thing, but it is a thing. And so now I have to be careful, right? So like when I go out, I have to monitor, because one of the things I actually notice as well is eating ice cream is a little tricky for me, because the cold of the ice cream will start to trigger that urticaria response in my throat, and I'll actually feel my throat kind of swelling up a little bit, like it's kind of closing off. So I have to eat my ice cream very slowly. I have to be very, very careful about how quickly I put that in, because if I take all the ice cream, all that cold, and it kind of swells my throat up, and I can kind of feel that. Now I've never blocked my airway or anything like that, but I can definitely feel that it's kind of getting swollen back there, which is one of the reasons why I always let my ice cream sit and kind of get a little melty, so that I can kind of take it at a bit of a lower temperature, and I kind of take it slowly. So, but this is something that was just acquired as a secondary consequence of that one particular infection. And if I had known what was happening at the time, I would have gone to the doctor and had them like test me for what kind of flu strain that was, that got me, that left that in there, because it was, I'm just, it's part of my life now, right? So it's just kind of the way I live, unfortunately. But it could be worse. I'm not complaining. It could be a lot worse. It's just a little annoying now, but it could be a lot worse, right? And so, like my hands in particular, like when I'm shoveling, they get really red and itchy and swollen. And then I have to kind of run them under hot water. And so when it cools down, then that speeds up the, it's like, okay, so we're good now. So I have to kind of like warm up quickly to kind of get that temperature down, so it doesn't trigger that cold urticaria. So it's just kind of a little irritating, right? Because I remember one of the times when I was working out, the way we found out was when I went outside, I came back in and I was like, had hives all over me. And my wife was looking at me like, what happened to you? I'm like, oh, that's why I'm itching. And I mean, literally, you could see like little red welts all over me. It's like, oh, okay. So, and I remembered that paper. It's like, darn, I guess I have cold urticaria. So, and that's it. So, so autoimmune diseases can touch a lot of us in a lot of different ways, right? And so it can be genetic, and like my case, it was environmental, I guess, in a way, right? So it's environmentally stimulated. And so it can also be due to infection. So another version of infection, other than mine, is a really, really bad one, rheumatic fever. So basically in rheumatic fever, you get a streptococcal bacterial infection. So oftentimes there's a couple of variants of streptococcal infection. We usually think of strep throat. That's a streptococcal infection. Also that invasive flesh-eating bacteria thing that we always like to read about, and this gory and stuff like that. That's a streptococcal infection that goes systemic and gets really aggressive. Rheumatic fever is another one. Now, the problem with rheumatic fever is basically what happens is it produces lots of antibodies against the streptococcal bacteria. And so, however, it'll also react with the heart muscle as well. And so when it reacts with the heart muscle, it's going to damage the heart muscle and the valves themselves. And so they will also make antibodies against the joints. And that's where you get this rheumatoid arthritis, right? So Mozart, one of my favorite composers, was actually in his biographies was known to have gone through several bouts of rheumatic fever in his life. One when he was a little kid, a really bad one. Oftentimes, this is referred to as scarlet fever. And so what happened was he got it as a kid, which basically means it probably did some damage to his heart. And he got it again when he was older as well. So he got 2 runs of rheumatic fever. And as a matter of fact, what we think Mozart died of at a very young age, he was only like in his mid-30s when he died, was heart failure. And the reason we think is because of the damage that was done to his heart through his bouts of rheumatic fever. And that's the reason why we think he died so young. But also, there are some stories as well. Even though Mozart was only in his 30s, One of the stories that we have actually comes from some of his friends. Mozart was considered the piano virtuoso's virtuoso, right? So, he was a piano master. That was his shtick, right? So nobody was better than Mozart when it came to piano. But later in his life, like right before he died, there was a story of him by his friends and his wife that was relayed of them at a dinner party where they said that Mozart, the great virtuoso of the piano, at that point, his hands were so arthritic that his wife actually had to cut his meat for him. And where did the arthritis come from? At the age of 30 something, probably as a secondary consequence of his rheumatic fever bouts. So he probably had a lot of damaged joints because of his rheumatic fever. And so that's probably what killed Mozart. So this is basically what it looks like. So when your joints get attacked, they start to get disfigured and painful and very difficult to move. So these are examples of arthritic joints. So when you see a person with these really gnarly fingers, usually an older person, not always, but usually an older person, that's usually what's happening. So their joints have just been compromised. Lupus, that's a common one, right? SLE, systemic lupus erythematosus. So this is basically another type of autoimmune disease. And so the damage is usually going toward the central nervous system, your nerves. It also goes after the heart, which is one of the reasons why we're concerned about lupus. And of course, the kidneys. So this can actually be fatal because you're going after some seriously core organs here, right? You're not going to mess with the cardiovascular system, the urinary system, the kidneys, and the central nervous system and get away with that. Right. So these are some really, really bad organs to do damage to. So oftentimes you'll see this as kind of a facial rash. Oftentimes it'll be accompanied with fever and joint pain because those are all the areas that are getting attacked. So what are they attacking? Well, what's happening is with lupus, you're creating antibodies against your own DNA. So pretty much every cell in your body has DNA in it, except for your red blood cells. So that's the reason why the lupus symptoms are spread throughout your entire body, because just about every cell in your body has DNA. This is a really bad thing to develop antibodies against, right? So this is a fundamental breakdown in that this is a good guy, right? You need DNA to live. You don't want to attack it, right? So this is a really huge breakdown. So basically autoimmune diseases are like a breakdown in the way your immune system is supposed to function and work. Kind of like a cop gone rogue, right? You've lost the fundamental ability to discern good versus bad. So other types of disorders that we see are things like myasthenia gravis, which basically will give you severe muscle weakness. And then it can be so severe at times where you can actually crash your respiratory system, right? Because your respiratory system relies on the contraction of your diaphragm in order to breathe. And if your diaphragm becomes so weak that you can't actually contract your diaphragm, you can just stop breathing, and that could cause death. Okay. So this is generally speaking when your antibodies start to go after muscles. So when you're attacking your own muscles or you're interfering with the function of your muscles, that's what's happening. Notice in all of these breakdowns, especially, notice what's happening is the antibodies in particular are misidentifying structures. Right? They're basically fundamentally forgetting that these are the good guys, these are the bad guys. Focus on the bad guys, right? So there's a really deep down fundamental breakdown in this tolerance training with these antibodies. So they're unable to discern clearly if you're going after your own tissues. That's not a good look. Multiple sclerosis is another big one. This is a breakdown in your T cell attack. In this particular case, what happens is your T cells are going after another normal tissue. It's going after your myelin sheath. So your myelin sheath is like insulation covering your nerve. So your nerve or your neurons have conductive components to them that are long and thin, the axons, and basically have an electrical impulse that goes through the axon or the membrane of the axon. But just like an electrical wire, where the electricity is going through the copper wire, in order to facilitate and to sort of make more efficient that transmission, you surround it with some insulation. So just like that insulating cover of a copper wire insulates the propagation of your electricity through your wire, so does the myelin sheath basically wrap around the axon and insulates the axon. And this basically allows that electrical impulse to efficiently move forward to its destination. Now, what happens is the T cells attack this myelin sheath. So essentially, you remove that nice, efficient propagation of the electrical signal. And what this can create is dysregulated transmission. So uncoordinated transmission, pretty much anything that touches that axon anywhere along its length can fire off a signal. It's not going in a particular direction or to a particular target anymore. It's just kind of randomly scattered all over the place. So this will create a lot of neural dysfunction and basically the dysregulation of your senses. For instance, double vision, because it's not communicating properly in your optic nerve. And of course, muscular weakness, because it's not communicating properly to your muscles to contract. Oftentimes, MS can be autoimmune, but it doesn't have to be. So we think it can be autoimmune, but we're not sure. The reason is we're not sure is because we haven't actually isolated anything specific that would trigger an autoimmune response, right? So most other things we can basically figure out some sort of an antigen that triggers this, but we haven't found that with MS. So why is it that the T cells go after the myelin sheath? We don't know. But again, the T cells, just like the B cells, just like the police officers, are all trained to tolerate self and to attack non-self. So in this case, both the T cells and the B cells and the antibodies are fundamentally not tolerating self tissue. We're not talking about abnormal myelin sheath, right? We're not talking about something that's weird and needs to be removed. We're talking about normal, healthy tissue being recognized as bad. Okay. So that's what we're talking about. So you can think of these sort of rogue cells, if you will, these cells that no longer recognize self versus non-self. Think of them in the case scenario. Think of them as active shooters, right? Who fundamentally have capacity to understand and perceive this of people good and not a, and then everybody. So fundamental breakdown, yes, and that's what's happening. It's like they're becoming the logical. Will to kind of immune. Okay. So to be. As I toggle over to our next chapter. So I should have like hold music here or something. Please hold while we are. So this next chapter, we're going to start with respiratory as opposed to digestive. So we'll do respiratory first, and then we'll move to digestive. And then from there, we'll go urinary and then skeletal and muscular system. So okay. The respiratory system. So basically, when we take a look at the respiratory system, we're going to see now in these next three systems, certainly respiratory, digestive, and urinary. We're going to see the systems themselves, but we're also going to see a cooperative effort between systems. So systems tend to be collaborators. They're not isolated. We just sort of put them in their own chapters just for sake of organizational purposes. But you're also going to notice as well just how much the cardiovascular system is interwoven into all these other systems, which is one of the reasons why we kind of have the cardiovascular system sort of as a central feature in the middle of the semester schedule, is because it is sort of the crown jewel of all of the systems of the body. Okay. So let's go ahead and sort of start scaling out, sort of sketching out a little bit of the respiratory system, its organization, and its functionality. So when we take a look at the respiratory system, what we're looking at now is essentially the system whose job it is to capture oxygen from the environment and also to expel carbon dioxide from the body. And the way we do this is through two different processes. The first one is inspiration or inhaling. This is basically going to be taking air from the atmosphere. It's going to be going into the lungs, and then where you can get access to the oxygen that's in the air itself. And then, of course, expiration or exhalation moves the air from the lungs to the atmosphere, the opposite direction. And this basically will expel anything that you need to get rid of or that you need to breathe out. So we're going to take a closer look at each of those two processes. But before we get there, let's kind of take a look at the general anatomy of the system itself. You can break the respiratory system into what's called the upper and the lower respiratory tract. So the upper respiratory is composed of pretty much all this stuff in your head, right? So basically you have, first of all, the nasal cavities, which is a big portion of your respiratory cavity. And the reason why I like this particular image is you can actually see how your nasal cavity is constructed. It's like a multi-story building with different levels. And so you have these different level floors, if you will, like this, and this, that forms the multi-layered structure of your nasal cavity. And then in between, you have these passages, these airways called meatuses, where the air basically flows through your nasal cavity. And so that is a huge part of the inlet of your respiratory system. You also have what's called your pharynx, which is essentially your throat, which is broken into three regions. And then your glottis, which is the opening into the trachea, and then the larynx, which is your voice box. Okay. So all those are basically part of the upper respiratory tract or the upper respiratory system. So getting the air into your head and then into the trachea. So once you pass the glottis and the larynx, that's your vocal cords and your voice box, now you're into the trachea heading to the lungs, and that's your lower respiratory tract. So the trachea is going to be the first piece of your lower respiratory tract. It's going to be going down through your throat and into your thoracic cavity. where it's going to be entering into a series of tubes. These are the bronchioles or the bronchus system. And then the bronchi, which are large tubes, will break up into smaller and smaller and smaller tubes until they get small enough to become what's called bronchioles. So this may look familiar to you. We had a similar type of organization with arteries, didn't we? Where you had larger arteries breaking into smaller ones and smaller ones until you got to arterioles, which are the smallest. And then, of course, the same thing you have here. You have bronchioles, which are these small little bronchial tubes that basically infiltrate and move into all of your lung tissue. At the tips of the bronchioles are essentially what's called your alveoli. These are the little air sacs, like little balloons attached to the ends of the bronchioles, and they are the ones that fill up with air. Okay. And then the last piece is going to be the muscle that makes it all happen, which is your diaphragm, a big bell-shaped muscle that actually forms the boundary between your thoracic cavity above it and your abdominal cavity below it. Okay. This is one of the reasons why if you punch somebody really hard in their little soft spot right here, which is about where your diaphragm is, you can kind of knock the wind out of them. That's kind of what you're doing. You're sort of like basically seizing up that diaphragm. So it kind of makes it a little harder for them to kind of get their diaphragm kind of back in order because you shocked their diaphragm with that huge blow. So ventilation is the mechanism that we look at of inspiration and expiration, or inhale and exhale. And so ultimately, you have to coordinate both your respiratory system with your cardiovascular system. Because the idea is your respiratory system brings the oxygen in, but your cardiovascular system is the one that has to transport it all. And so your transporter basically has to take the oxygen from the lungs, and then it has to transport it to the tissues, where it'll pick up carbon dioxide from the tissues and then take that back to the lungs. So you can see that you have to coordinate this intake of oxygen and this exhale of CO2. You have to coordinate this with your cardiovascular system so that you can basically have the distribution of these molecules throughout your body in the way that you want them distributed throughout your body. Okay. Now, in cellular respiration, this is basically what happens in the mitochondria. That makes your energetic molecule, which is ATP. That's like your rechargeable battery. That's what fuels all of the energy requiring business of your cell and your physiology. So you have to have that, right? Just like your cell phone isn't going to be functional to you if you don't have a charged up battery in your cell phone, right? And so you have to keep recharging that. So ATP is like your rechargeable battery. And so you have to keep making ATP in order to keep fueling all those energetic demands of your cell. So during this process, what happens is you use up oxygen in order to make the ATP, and as a byproduct, you produce CO2. So your tissues, who are busy doing cell respiration, making ATP, making that energy, are essentially going to be consuming the oxygen that you deliver to them, and they're going to be making the trash, right? The byproduct, which is going to be the CO2. And you got to carry that CO2 away, the trash, right? So ultimately then, when you take a look at your respiratory system in kind of a stepwise fashion, the first thing you're going to get is your external respiration, where you're going to be exchanging gases, oxygen and CO2, and that's going to be happening between your lungs and your blood that is in the lungs. Then once you pick up the oxygen, you're going to transport that from the lungs to the tissues who need the oxygen. And then once they consume the oxygen, they're going to create CO2, and you're going to get another exchange of gases, and you're going to transport it back to the lungs. Then in internal respiration, basically, you're going to get that exchange of gases between the blood and the tissue is going to burn that oxygen in the production of ATP, generating CO2, which is picked up by the blood, and then it brings it back to the lungs for exchange. So you can see you kind of have a cyclic type of an exchange system. This is kind of what it looks like. So essentially what's going to happen is you're going to have your air coming into your lungs, and between your blood and your lungs, you're going to have the pickup of oxygen. So here you can see the oxygen being picked up by the capillaries in your lungs, and they're dumping off the CO2 into your lungs. And then you exhale the CO2 so into the outside atmosphere, and you inhale the O2. So whenever you exhale, you're getting rid of the CO2. Whenever you inhale, you're bringing in more oxygen. Then what's going to happen is the blood is going to take that and it's going to go to the tissues where it'll deliver the oxygen to the tissues who need it the most. Their waste, which is the CO2 made from that cellular respiration, will then be loaded onto the blood. So the blood will then take that and it'll basically move it on back to the heart, where it'll be repumped back through the lungs for gas exchange, where you do it all over again. Okay. Now, we'll see this image again as we get to digestive system. So we'll highlight this piece over here. And then also when we get to the urinary system, where we'll highlight this piece here. So we'll see the whole full trajectory of the distribution of blood as it goes throughout the body. So you can see how the cardiovascular system is pulling together several major systems as it sort of goes throughout the body and makes all these different stops. Okay, so let's go ahead and start with our close-up view. That's just sort of the general sketch out of the respiratory system. Now let's take a look at our close-up view of the anatomy, starting with the upper respiratory system, then we'll work our way down, and we'll take a look at the process of ventilation and kind of what's happening there, so how that's working. So the big three of the upper respiratory tract is the nasal cavities. That's number one. Of course, the throat, the pharynx, and of course the larynx, the voice box. So if you kind of take a look, kind of an up close view, this is basically the same image we saw before, only now we've kind of cut it in half for upper respiratory, and we have essentially blown up the view of it. So you're basically going to be taking air through what's called the nares. So that's basically the fancy term for the nostrils. And so you can see your nasal cavity is here. So you can see that multi-level nasal cavity structure. But you can see that the nasal cavity is bounded by this bony structure here, which is actually your maxilla. This is your palate. So you have a hard palate and you have a soft palate, which is this fleshy piece at the back end of your palate. So if you run your tongue across the top of your palate, you'll feel the hard palate first, and then you'll kind of feel like a little soft dip. That's the soft palate. So that's basically where the maxilla has stopped, and that new membrane now is a soft palate. So your palate in general is separating your nasal cavity from your oral cavity. This is one of the ways that you keep food out of your nasal cavity, right? So that the two don't mix together. So then as you start to move back, you'll start to run into the pharynx, which has a couple of different pieces. So for instance, you have regions of the pharynx, three of them actually. You have what's called the nasopharynx, which is a region of the pharynx that's right behind the nasal cavity. And generally speaking, right at this little junction area, you'll see a tonsil, right? Tonsils are lymphatic tissue, right? Designed to basically do battle with pathogens as you inhale them. You'll also notice like a little opening right there. This is basically where you can get drainage into the back of your throat, right? And so a lot of times when you're talking about post-nasal drip, you may ever dance with that one. It oftentimes will cause a sore throat, right? And so the first question is, well, what's causing your sore throat? Is it just kind of like a post-nasal drip thing, or is it like strep throat, like a bacterial infection or something like that? Well, what post-nasal drip basically is as you are battling with and inhaling air and you're doing battle with like cold or something like that, you're going to build up mucus in your nasal cavity. So these layers are covered with mucous membranes. And so as you get infected with something, those mucous membranes become more active so they can capture more of those pathogens. And then you have to either expel that excess mucus by either blowing your nose, or a lot of times what'll happen is the mucus will drain down the back of your throat, right? And there's a lot of us who hate that feeling, right? But a lot of times, especially if you have a really bad cold, I mean, it kind of almost feels like you're drowning, because it's like there's just so much that's just clearing out of your nasal cavity and going down your throat, and then a lot of times you'll also get drainage going down your throat, and you won't even know it's going down there. It's just a slow trickle. But sometimes what'll happen is some of that will start to, a lot of it will go down your esophagus. The idea is you're trying to get rid of it, right? It goes down your esophagus. Some of that, however, especially if it's not a lot, will kind of make its way into the trachea a little bit. And this is kind of where you start to get that throat clear thing, where you kind of start to get a little bit of phlegmy buildup. in your respiratory system, and you have to kind of cough it out all the time. That's because you have a little bit of drainage going on back there. And so that's kind of what your nasal cavity is designed to do. That's the way it's supposed to work, by the way. It may feel nasty. You may not much care for it, but that's actually the way it's supposed to work, is that excess nasal discharge is designed to just passively drain out through the throat and then into the stomach so that you don't even know it's there, right? Because part of the problem is when you blow your nose, in reality, it's not very effective because most of what you're blowing out is going to be right here in the front region. You're not really getting the majority of that nasal cavity discharge. Most of that's going down the back. Okay. So that was lovely, wasn't it? That was an enjoyable. Now you guys know what's happening when you guys have a bad cold. Okay. So that's the nasopharynx. The oropharynx is the region of the throat that's right behind the oral cavity, right? And so you have a couple of tonsils here as well. So here's another tonsil right there. That's the one you can see when you open your mouth. You go, ah, right? That's the one you can see on the sides. And so this one basically is where you have the food bolus that comes in. So when you're chewing your food, you basically push the food to the back of your throat with your tongue. It passes your uvula, which is the very tip of your soft palate, and then it goes down your esophagus through your oropharynx. Now, the idea is if you've ever had milk come out of your nose, we've all had that, right? Anybody ever shoot milk out your nose? We wait until you take a drink, and then we tell you something really funny. And then what happens? It all comes out. What happened there? Well, what happened was you were in the process of swallowing that milk or whatever it was. And then when you laughed, a big expulsion of air came out of your trachea and pushed all that fluid through your nasal cavity and out your nose. Right? Not terribly, not really all that pleasant. Right? Or if you've ever got pool water in your nasal cavity, anybody ever snort the pool? You're out there. Don't hide. I know you're out there, right? You do that all the time. It's usually because you're breathing, your breathing is off or something like that, or you happen to get a big splash of water right when you're taking a breath, and it gets up in your nasal cavity. It hurts, right? But that's basically up in your nasal cavity, and then you're kind of like coughing and swallowing at the same time, right? Right. The idea, it's good to swallow, by the way, because if you don't swallow, it's going to go down your trachea, and then you're going to be coughing, right? So some of us have probably got that nasal cavity water in there, and we've kind of like had to sort of like get it back in there so that we could actually swallow it down so it doesn't choke us the next time we go under, right? Because you don't want to passively drown. That's not cool. Or actively drown for that matter. And then as you start to go down, you have the laryngopharynx, which is basically right behind the larynx. That's behind the voice box. So that's kind of the beginning, if you will, of the boundary between the upper and the lower respiratory section. And so here you can see on top of your glottis, which is your opening to the trachea, is going to be the epiglottis, which is a piece of cartilage that basically closes off your trachea when you're swallowing. We'll talk more about that actually when we get to the digestive system. Because we're going to see this again, by the way. Because in the next chapter, when we get to digestive system, we're going to see this again. Why? Because the same structures of the digestive system are also in the head. So we're doing both digestion and respiratory at the same time, right? Nasal cavity is respiratory, oral cavity is digestive system. Okay. And then we basically pass this air over our larynx, which is our voice box, and then it goes down the trachea. So let's go ahead and start with the nares, right? So the nares basically is the nostrils of your nose. And so this is basically the passage of air as it goes into the nasal cavities itself. And so the nasal cavities have these bony cartilaginous septa. Those are those layers, right? And these are actually skull bones that actually create these layering systems. And also, they're covered with mucus membranes. And in them, in that epithelium, because mucus membranes is a type of epithelium, you're going to have little hairs, right? Little hairs that are in there. And their job is to filter the air and to trap small particles in the air. This is one of the reasons why when you breathe, the ideal way to breathe is through your nose. Your nose does a couple of things with the air. So the mucus, first of all, is going to trap particles that you're breathing in. So if you're breathing in dust and things like that, those dusty particles, those dirt particles are going to get stuck in that sticky mucus. And that basically will stick there until you can remove them. Either you can remove them to the pharynx, where they are swallowed or spit up. That's expectorated, right? That's a fancy term for just hawk it out. Or they can be swallowed or blown out. Now, under the mucus layer is what's called submucosa, which typically is a connective tissue region, but in this particular case, your submucosa has lots of capillaries. Now, remember what we mentioned before. Blood is hot, right? That's where our body heat comes from, is from our blood. And so in that submucosa region, just underneath the mucous membranes, is going to be a capillary-rich layer with lots of heat. This basically helps you to warm that incoming air. So you have a couple things happening here. First of all, the air that you breathe in is being cleaned up by all those particles being trapped in the mucus. Why? Because the air that gets into your lungs, you want to be as clean as possible. You don't want a bunch of debris and dirt in your lungs, right? Because bad things happen. You can create respiratory failure when you do that. As a matter of fact, this is one of the common things that happens, one of the common side effects of people who go through like tragedies, for instance, like volcanic explosions, or who go through fire is a good one. That's the reason why firemen have to wear those masks, those ventilators. It's not just because it smells and they can choke on the smoke, but because what happens is a lot of those smoke particles can get into the lungs because they can't trap all of it and get it all out. A lot of that's going into their lungs, and when it gets into their lungs, it interacts with the fluid in their lungs. There's a little bit of fluid in there. And the body fluids it can interact with, and ash and body fluids basically mixes together to create a kind of a muddy paste, which can lodge in your alveoli, those air sacs, and it can basically block your airways. People who go through volcanoes will oftentimes inhale the ash of the volcano, which is a little bit different, right? In a fire, the ash is mostly incinerated wood particles, right? In a volcano, the ash is mostly pulverized rock ash. It's basically, if you want to know what volcanic ash is like, it's essentially like cement powder. And when you inhale that, when you mix, if you've ever bought, has anybody ever bought a bag of like quick dry cement from like Home Depot? You open it up, it's a really fine powder. You don't want to inhale that stuff, right? What do? You mix it with a little bit of water and it creates cement. So when you're inhaling that pyroclastic flow, that volcanic ash, that's basically powdered rock that you inhale, mixes with your body fluids, and it basically turns into cement. And that will destroy your lung tissue. As a matter of fact, people who go through these sorts of things oftentimes have chronic respiratory problems. It happened to the people in the Dust Bowl, where a lot of dirt, those big dust storms came off of the plains and basically swept big clouds of dust. I mean, people's houses were full of dust. You've actually got pictures where people would actually have like layers, thick layers of dust in their house. They'd sweep it out and it would just come right back in. And their houses were like, it was like a fog bank of dust. This is what these people were living in. And they had to sort of reduce that as much as they could by putting up wet blankets to trap some of that dust. And that made it a little bit better, but there was dust. Everybody's inhaling dust. And those people actually had massive respiratory problems after the Dust Bowl went through. And so whenever you have something like that, that's why you have to cover up, because that stuff gets in there and it can cause a lot of problems. It's the reason why you have these mucous membranes in your nasal cavity to trap all those dust particles so that it doesn't get into your lungs. You want that pure air in your lungs. You don't want a bunch of debris in there. Okay. The other thing is also you want to warm the air and moisten it. The air can be dry. Your lungs are not. So if you put dry air in wet lungs, guess what's going to happen? That dry air is going to suck all of the moisture out of the lungs, and it's going to dry up your lungs, and it's going to make them difficult to function properly. So you send it through your nasal cavity to moisten the air with all those wet, drippy mucous membranes. By the way, have you ever noticed, I talk noses again, have you ever noticed that when you're out in the cold air, your nose starts to run? The mucus in your nose gets thinner and more watery in nature. Do you know why? Because what you're trying to do is you're basically trying to do exactly this. You're trying to moisten that dry. Because usually, especially in Denver, right, the cold air is also the driest air. Winter is our dry month, right? That's the driest month. How do we know that? Because in those winter months, we all start turning into lizards, right? And the lotion stock on the market goes way up. Buy Jergens or whatever, right? Dove, whatever your favorite lotion is. Make lots of money, right? Because this is the dry season. And so as the air goes into your nasal cavity, it's trying to moisten that air so that it doesn't dehydrate your lungs. It's also trying to warm it, because if you breathe in cold air, it's going to hurt. By the way, it does, doesn't it? Have you ever gone jogging like in freezing weather, in cold weather, and you're sucking in all that cold air? Because when you're jogging, you're not breathing through your nose, are you? You're breathing through your mouth. So now all of a sudden, you're not warming the air quite as well. And so as a result, you've got cold air going into your lungs, and your chest starts to hurt because that cold air is going into your lungs, right? So that's the reason why you warm it and you moisten it. So now, because you got a lot of capillaries in that submucosal region, when you do hit that dry air, what happens is all of those capillaries are basically trying to warm the air. Your mucus is pulling moisture from your body to moisten the air. But then what happens is those capillaries oftentimes will dry up and crack, just like your skin, right? And when they do, they'll burst the capillaries, and of course, you get nosebleeds. This is the reason why, have you ever noticed that you tend to get more nosebleeds in the winter than in the spring or summer? That's because of the dry air. Drying out your membranes, and that compromises the capillary structure, and the capillaries burst, and you get a nosebleed. Okay. So all the things you wanted to know about your nose, and then some, more so than you ever wanted to know about your nose, right? So now you guys can be a rhinologist. You're like, no thanks. It's an ENT, right? Ear, nose, and throat. That's who takes care of the nose. So just rhino is the word for nose. So technically an ENT is 1/3 rhinologist. So they do the head and neck or ear as well. So also in the nose, you have receptors in the surface, in the very upper portion of that nose. Why? Because up here, notice what's basically sitting and separating the upper portion of your nasal cavity from your brain. So this is your brain. Your frontal lobe is up here. Sitting right here on top of this region right there, which is what's called the ethmoid, it's the skull bone, is one of your cranial nerves. It's one of your sensory nerves. It's called the olfactory nerve. It's your smell. And in this bone, you see these little itty bitty holes. Those are called what's called cribriform foramina. So this little bony plate right here is what's called the cribriform plate. It's actually the bottom portion of one of your skull bones, and it has little holes in it called cribriform foramina. And in these little holes, you see little nervelets dangling down in there. Those are basically your olfactory nerves. And so they have receptors, smell receptors on them. So when you inhale, all those molecules will attach to those receptors, and you'll be able to interpret that as a sense of smell. And so that's basically what you have in that particular area, those odor receptors in that upper portion of your nasal cavity. You also have your tear glands basically will also drain into your nasal cavities. So your tear ducts are actually connected into your nasal cavities themselves. Let me see if we have, we don't have that cutaway here. This is one of the reasons why you get all snotty when you cry. Is because those tears are draining down into the nasal cavity. Notice the strategy. You're producing lots of fluids in and around your head region. And where are they all draining? Nasal cavity. And that nasal cavity drains to the back of your throat, which then goes down the esophagus to your stomach. Right? So it's all kind of interconnected. You also have little openings in some skull bones called sinuses. And you can get fluid accumulating in these sinuses, and that causes pressure, your pressure headaches, right? Your sinus headaches. That's basically what's happening. If you get a little headache right here, it feels like it's right between your eyes, right? That particular headache is going to be associated with what's called the frontal sinus. It's actually lodged in your frontal bone, which is your forehead, right? So you got a sinus right there. You also have what's called maxillary sinuses. So you got a pair of sinuses that are right here underneath your eyes. So sometimes you can feel those. You can feel pressure in there. And you have another one called the sphenoid sinus, which is basically at the back of your nasal cavity. And sometimes that can fill with fluid as well. So these are there's a couple of reasons why you have sinuses. And so the first one is typically for purposes of resonation or resonance, if you will. It's sound, vocalization, right? That's a big one. A lot of other mammals actually have this as well. Whales have this. They've got big chambers in their skull bones, and they're using these for resonating their voice. This is basically one of the reasons why your voice sounds much better in your head than it actually does to other people, right? So the same thing is also true for our sense of vision. So the way we see ourselves in the mirror looks a lot better than the way the other people see us. Which is one of the reasons why when you see a video of yourself, it's like your voice sounds weird to you because you're hearing it the way other people hear you, which is always frightening to me because I play some of these videos back and I hear myself. I'm like, wow, my poor students, I should like give them all like 10 points just for having them endure listening to me, right? It's like, you know, and then you look at yourself and you're like, who is that? You know, have you ever done that? You looked at a video of yourself and you're like, that me? That doesn't look like me. I look much better than that, right? It's always that way, isn't it? Right? It's always like, no, I look better than that, right? Because there's kind of the same sort of delusion thing going on in your brain when it comes to sight, right? So you kind of have the same thing. You have this definite view of yourself from the inside out versus from whatever people see from the outside in. And so this is actually a very common public speaking trick, right? A lot of times people in public speaking will say, you know, a couple of things. I'll say, get in front of a mirror and watch yourself in a mirror so that you can kind of manipulate how you talk and your facial expressions and how you're communicating, right? That's why you talk to yourself in a mirror when you do a speech, is to master that sort of thing. So it becomes secondhand. So when you're doing it, it's like you're automatically doing it and it makes you a good public speaker. The other one is videotape yourself. So you can watch yourself as the way other people see you, right? And you can hear yourself the way other people hear you, right? So it is common for people to be in love with the sound of their own voice because to them it sounds great. To everybody else, it's like, can you please stop? Right? And so it's a very different experience. But the reason is because our voice is being produced from inside of us and it's resonating through these empty chambers in our skull, including our sinuses. And so part of that creates this sort of tonal quality that we ourselves hear, and we hear our voice from inside, not from outside, right? So we don't hear our voice coming out and then we hear it coming back in. That's not the way we hear it. We hear our voice from inside as it comes out. That's the reason why our voice sounds different to us when we hear it recorded back to us, is because we now don't have the luxury of hearing that voice as it resonates through our echo chambers, which are our sinuses. Okay. So we always sound better in our head than we actually do in real life. And every time I'm working with anybody, or like when I'm making video things like that, I always try to keep that in mind because it's just like, wow. It always amazes me how much people are willing to put up with me, because I'm like, it's like, I like watch my own videos. I'm like, I don't know that I could sit for my own class. I mean, I don't like what I'm seeing. I just zone out. You guys are fun. I know you guys are right there with me. You know exactly what I'm talking about. And that's okay. But it's just because it's like, wow, that sounded so much better in my head than it actually sounded coming out. Right? That happens a lot. Singers run into that a lot. Right? You just have to get over it. So ultimately, then, the air will go through the nasal cavities. It'll move through the nasopharynx into the upper portion of the pharynx, and then it'll go basically down into the trachea as it starts to move through the larynx. We'll talk about the larynx here in just a second. One thing we do want to mention, however, is an area in the same region that's important, that's called the auditory tubes or the eustachian tubes, right? This is actually a piece of what's called the middle ear. It's in the nasopharynx area, and the eustachian tubes are actually connected into the nasopharynx. And this is typically mostly in the middle ear. It's mostly air. So there's air normally in your middle ear. This is where those little auditory ossicles are. Some of you may have run into things like hammer, stirrup, anvil, those sorts of things that are just on the other side of your eardrum. They're part of your ability to hear, and it's mostly air just behind that. And connected to that air pocket in your middle ear is the eustachian tube, which basically comes down your neck and then enters into your nasal cavity. Okay. And so typically when you have air pressure changes, this is what causes your popping ear. Because as you change pressure in elevation, that pressure builds up on the outside, but the pressure on the inside is the same. And then in order to equilibrate with the outside, your ears pop, allowing your atmospheric and your internal pressures to equilibrate. And that's what's happening when your ears pop. Okay. However, when you're sick, these eustachian tubes can also get plugged up, right? So because your nasal cavity starts to get really mucousy, a lot of that congestion can back up into the eustachian tubes, plugging that pressure in the eustachian tubes, which creates pressure on your ears. You ever felt that sensation? Bad cold, you get pressure on your ears. And that can get up into pretty good ways into your ear. And that's kind of where you start to get to ear infections and things like that, is because it's hard to get that out of there, because it's not designed to be plugged up like that with a bunch of nasal discharge, which typically is a pretty dirty discharge is usually. So you're not trying to send that up there. It's kind of getting backed up in there. And that's one of the reasons why, if you've ever had that kind of muffled sound, like when you're really sick, it's like you can't hear anything. Everything's muffled. And then you can hear when your eustachian tube clears out. Why? Because as soon as your eustachian tube clears out, all of a sudden everything gets really loud and echoey. It's like, whoa, okay, I can hear. It's like somebody just turned the amp on, right? That's because your eustachian tube just drained out, and now you've gone back to normal hearing. Okay, that's kind of what's happening with that. So just a lot of revelations here in terms of stuff that happens to us all the time, but we don't ever think about it. So then we get to the pharynx. So now that we're in the pharynx, we're in the throat area, right? It's kind of like a funnel-shaped sort of a situation. So the nasal cavity is going to connect right behind the oral cavity. So the two of those connect together into the pharynx proper. Of course, we have our naso, oro, and laryngeal pharynx. This is basically just defined as where that particular region of the throat is. And of course, peppered throughout the pharynx, we have our tonsils, which are oftentimes at the junction of both our oral cavity, and of course, we've got one in our nasal cavity, the nasopharynx. And this is, of course, because the lymphoid tissue is essentially fighting off pathogens, right? So anything that you inhale, that's a pathogen. Or in the case of the oral cavity, anything that you eat, that's a pathogen. It's doing battle there. So the larynx. So the voice box. Let's go ahead and take a look at the voice box. So what's in the voice box? So the voice box basically is a cartilaginous structure, and this is going to be essentially right at the beginning of the trachea. So it kind of is the boundary between pharynx and trachea. It's hidden behind what's called the laryngeal prominence, which is a big piece of cartilage. It's actually what's called thyroid cartilage. It's your Adam's apple, right? Or what my dad used to call the gully whopper. which is not a technical term. Don't try that one on a board exam or anything like that. Just right. That is covering your voice box, that big piece of cartilage right there. Okay. And so this is basically where you're going to have your vocal cords, which are basically mucosal folds, little folds of tissue, and they have elastic ligaments that are sort of supporting those folds. And so when you take a look at this, slit between the cords, and the slit or the opening we call the glottis. Okay. So when the air passes over these cords, then the cords will vibrate, producing a sound. Very similar to a guitar string. Only it's kind of like, and I only say that in terms of because we know a guitar string, probably most of us are familiar with guitars. And we know that when you pluck the string, you're creating a vibration that creates a sound, right? And in that sense, you're doing the same thing with your vocal cords. But in reality, a vocal cord is a little bit more like a reed instrument, especially my favorite reed instrument, which is the oboe. And that's the one I play. Not very well. I just like to play with it, right? But an oboe is a reed instrument that has what's called a double reed. So you have basically two reeds that are kind of tied together on each other. And what happens is these reeds, you put your lips right here. So those are your lips. And you basically blow the air. Those are lips. It looks like an anteater is hanging on this thing. But you blow the air across these reeds. And what happens is these reeds will vibrate back and forth, creating a sound. And of course, you have holes in the oboe as well. So those reeds are basically like this. And when they blow air through them, they vibrate back and forth, creating the sound. And of course, your lips are pursed on them like this. As they're vibrating back and forth between your lips, it's creating a sound, and you're using your lips to kind of form and round out the tone of the sound. And the air goes through the oboe and through the holes to produce a particular pitch. However, the reed by itself, if you blow on it, is able to actually produce a sound by itself, right? And so usually that's how oboists tune the oboe. They carve their reeds so that it's a C, right? That the actual tone that they blow into it is a C, okay? And so that's basically how this is happening with your vocal cords, because you got two of them, and as you're pushing air across them, you're vibrating them very much like a double reed, and basically that's creating the tone or the sound. But just like the oboist lips, you're also able to sort of pinch down on the vocal cords and create like very different types of vocal sounds with those cords. Okay, just like you can create very different types of sounds with your lips on an oboe as you sort of purse your lips on the oboe reed itself. So if you basically create a greater tension, you're going to get a higher pitch. If you open up the glottis, then you're going to get a lower pitch. And now the loudness basically is depending on the amount of vibration that you get. If you want to do a very soft sound, you blow into the reed very gently. You'll get a very nice, soft, mellow sound. If you want to blast it like a big horn, you just boom, you blast a puff of air in there, and it's going to really make it loud, right? So these are all things that you learn about, especially when you do a reed instrument, or you learn how to play a reed instrument. This is what it looks like. So here you can see your two vocal cord folds here on either side. So here's your two vocal cord folds here. So that's your strings. The opening is your glottis. So there's your opening. You can see down inside is your trachea. You have the base of your tongue just above, and your epiglottis is just above that as well. So you can see this is literally right next to your tongue. And so as the air comes through it, then you can basically pinch down on your vocal cords, and you can cinch down on it kind of in a similar way that you form a whistle, right? So what you're doing with a whistle is you're tightening the hole or the aperture with your lips, right? By pursing it down, that creates a higher pitch. If you open up the hole in your lips, you're creating a lower pitch, right? You're doing this exact same thing with your vocal cords. So what happens when you swallow food? Basically, when you swallow food, your larynx will move up. It'll basically push up against the epiglottis, which covers the larynx. And so this basically will cover up the larynx and disallows food from moving in to the trachea. So if everything's going well and you're swallowing and you're not inhaling your food, then your food that's going down should land on top of that larynx. And if you take a look at this image here, so the food will come down, it'll push that larynx down. That larynx will fold over the top of your trachea, covering the glottis, and that only leaves one pathway for your food to go down, and that's down the esophagus, protecting your trachea from having food go down your trachea. When you choke, what happens is you have food that's just above the epiglottis, that hasn't hit the epiglottis yet, and what you do is you do an inhale. You laugh, and it basically goes down your trachea because it didn't hit that epiglottis. Okay. So that is the larynx, and then next time we will start moving. This is a great place to start, actually, right? Because we'll start our lower respiratory tract stuff. We'll do that on Monday.